So this is section 6.2, series solutions continued. So we are going to solve y double prime minus y equals 0 with a couple of conditions. Y of 0 equals 3, y prime of 0 equals 5. We're going to solve that using sigma notation, and our goal is to find the first 6 non-zero terms. So let's remember what y looks like. It's a power series, sum from n equals 0 to infinity, of terms that look like Cn x to the n. If we want to figure out y prime, we're thinking about taking the derivative term by term. So we'd have a series that looks like n Cn x to the n minus 1, only that series gets summed from n equal 1 to infinity. So we actually don't put the n equals 0 term in there because it would be a 0 term. So we're fine to just exclude that and start our series at n equal 1. The reason that we want to exclude that n equals 0 term is that it would have power x to the negative 1, and that's going to make some of our algebra a little bit more complicated. So let's exclude that term that would look like 0 c0 x to the negative 1. Similarly for y double prime, we are taking the derivative term by term of y prime. Have the sum of terms that look like n times n minus 1, cn x to the n minus 2, and then we're going to think about what indices we want for that sum. We're actually going to go from n equal 2 to infinity. So similar kind of discussion as we had for y prime. We're going to be excluding the n equal 0 and n equal 1 terms because they are 0. The n equal 0 term would be 0 c0 x to the negative 2. The n equal 1 term, 0 c1 x to the negative 1. So it's valid to exclude those because they are 0, but the motivation for excluding them is that we don't want to put the negative powers into our power series. So let's write down that we're just excluding both those terms, and that's why that series starts at n equal 2. So then let's see what happens if we sub into our dE. Remember that our dE is y double prime minus y equals 0. So we would have the sum from n equal 2 to infinity, n minus 1, cn x to the n minus 2, minus sum from n equals 0 to infinity, cn x to the n, and that is equal to 0. Okay, now our goal here is to make it so that both series have the same exponent. So we're going to do a change of variables. We're just going to give the exponent for both series a new name. Let's call it k. So for the first series, k is equal to n minus 2. And let's think about what k values that series is going to be running through. Well, an n value of 2 corresponds to a k value of 0. So that means when we rewrite our series in the language of k, that series is going to be starting at k equals 0. For our next step, it might be helpful here to actually solve for n in terms of k. So solving for n would be k plus 2. Same kind of idea for the second series. K is just the name we're giving to the exponent. So for that series, k is equal to n. If n equals 0 is our first term in our series, that means k equals 0 will be the first term in the new series when that gets rewritten in terms of k. So the plan now is to rewrite both series using k, and the rule is that all series are going to start at the biggest k value. So if we look back over our previous work, that first series is starting at k equals 0, second series also starting at k equals 0. So what's the bigger of those two k values? Well, it would just be k equals 0, so that's where the new series are going to start. All right, so let's do our rewriting then. So that first series starting at k equals 0, so going from k equals 0 to infinity, n we decided was equal to k plus 2. So as we sub that in, we've got sum of terms that look like k plus 2 times k plus 1, c sub k plus 2, x to the k. Now for the second series, k is equal to n. So when we rewrite that in terms of k, we're going minus the sum from k equals 0 to infinity, terms that look like ck x to the k, and that whole thing is equal to 0. So now we've successfully created two series that both have the x to the k in them, and that's going to allow us to compress this just into a single series. Notice also that both series run through the same k values. So we're summing from k equal 0 to infinity for both series. So we can go sum from k equals 0 to infinity of, well, we might as well factor out the x to the k because it's going to be in both the terms that we are summing up. So k plus 2, k plus 1, c sub k plus 2 minus c sub k would be what goes in the square brackets here, and that's equal to 0. Now we saw a rule in our first series problem for how to proceed from here. The idea is that on the left side, we basically have this infinite polynomial, and we're saying that's equal to 0 for any x value that we plug in. So if that's the case, then it must be that the coefficients are equal to 0. Each coefficient here has to be equal to 0. So the plan is to set the coefficients equal to 0, and we'll see how that helps us figure out the coefficients of this power series. So by setting the coefficients equal to 0, we're saying that k plus 2 times k plus 1, c sub k plus 2 minus c sub k is equal to 0. And what we do here is we solve for the coefficient with the higher index. So we want to solve this for c sub k plus 2. Okay, so we could bring this ck over to the right side there. We'd be dividing by k plus 2 times k plus 1. And this formula here is valid for whatever k values our series is being summed through. In this case, summing from k equals 0 to infinity. So we could just write here, this would be valid for k values at least 0. So the overall plan now is to figure out the values of C0 and C1 using those initial conditions that were given in the question. And then this equation here, by plugging in our different k values, this is going to give us the values of C2, C3, C4, C5, so we can generate as many terms as we want to. So let's take a little detour here. We'll think about C0, C1, and then we'll come back to this equation here when we're ready to get C2, C3, etc. So remember our series y had the form y was the sum from n equals 0 to infinity, cn x to the n. That's just an overly formal way of saying y is equal to c0 plus c1x plus c2x squared, etc. So let's think about those initial conditions. We were told that y of 0 was equal to 3. So if we plug in y equals 3, x equals 0, that tells us that 3 is equal to c0. We also have some information about y prime, so let's think about what y prime is. It would be c1 plus 2c2x, etc. So subbing in a y prime value of 5 with an x value of 0 would get 5 equals c1. All right, so we figured out c0 and c1. Let's write this in a bit more organized way. So c0 is 3, c1 is 5, and then we're going to use that equation from a minute ago to figure out the other k values. So let's just scroll back for a second. Recall this formula here that applies as soon as k is equal to 0, 1, 2, 3, etc. So I'll just write down that equation. That's called the recurrence relation. So the recurrence relation that helps us generate the future coefficients is that c sub k plus 2 is equal to c sub k divided by k plus 2 times k plus 1. That is valid for k greater than or equal to 0. So if we sub in the k value 0, we're going to get the value of c2. If we sub in the k value 1, we're going to get the value of c3, etc. Then we can look back at the question and see how many terms we were asked to find. So we'll just scroll back for a second. We were asked to find the first 6 non-zero terms of the power series solution. All right, so let's think through how much calculation we're going to have to do here. At this point, we would have the first 4 coefficients, so we'll need to do 2 more. We'll need to go up as far as C5. So just by sequentially plugging in different k values, we'll get those values for our coefficients. So let's try it. Plugging into our recurrence relation right here, value k equals 0 getting subbed in tells us that C2 is equal to C0 divided by 2 times 1. C0 is 3. So in other words, we've got 3/2 for the C2 value. Okay, C3, according to the recurrence relation, is C1 over 3 times 2. C1 is 5, so that would be 5 over 6. C4 is going to be C2 over 4 times 3. So we could say that's 1/12 of whatever C2 was, but C2 was 3/2. So we get 3 over 24, or we might call that 1 over 8. C5 would be C3 over 5 times 4. So that's 1/20th of whatever C3 was. We figured out that C3 was 5 over 6. So we could call that 5 over 120, or that actually simplifies to 1 over 24. So there we have our coefficients. And remember, the form of our series solution was y equal the sum from n equals 0 to infinity, Cn x to the n. If we write that less formally, we're just saying y is C0 plus C1x plus C2x squared plus ... So now we've got all our coefficients, and we can just write out the first 6 non-zero terms of our solution. So our first coefficient was 3, next one was 5, then we had 3/2, so that would give us a 3/2 x squared, and we're just going to continue like that using the appropriate coefficient with the appropriate power of x. So next we'd have 5/6 x cubed plus 1/8 x to the 4th plus 1 over 24 x to the 5. And there we go. We figured out our first 6 non-zero terms of a power series solution to that particular DE.